Good morning, friends. Today we are going to see about KCL and KVL. So while solving the problems and the understanding the concepts of KCL, before that we are supposed to know about how the series resistance has been connected. The components are connected into U and the total resistance is the sum of individual resistances. Current remains the same across all components, so that R total has been written as R1 plus R2 plus R3 etc. Rn. So in parallel circuit, the resistance has been connected, components are connected across common points and the total resistance is calculated using the reciprocal of individual resistance. Voltage remains the same across all components. So 1 by R total is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. 1 by Rn. According to Ohm's law, the relationship between voltage, current and resistance are expressed as V is equal to I1 to R, or else we can write I is equal to V by R. It helps calculate the voltage, current or resistance. When two of these values are known, the other value has been calculated automatically. So V is equal to IR, which is current law. It has been called as the junction rule. Kirchhoff's current law is a fundamental law that is based on the principle of conservation of charge. It states that the total current flowing into a junction or node in a circuit is equal to the total current flowing out of the junction. The total current flowing into a junction or node in a circuit is equal to the total current flowing out of the junction. Here summation of current in, that is input current, represents the summation of all currents entering the junction, and summation of current out represents the summation of all currents leaving the junction. The summation symbol sigma denotes the summation operation in mathematics, that is addition operation, indicating that we are adding up multiple related quantities. Let us consider the diagram. Here there are 5 currents that has been represented by letters I1, I2, I3, I4 and I5. From the figure we can understand that the currents I1, I2, I5 are flowing towards the node capital A, and other currents, that is I3 and I4, flowing out of the node from capital A. If you assume passive sign convention such that the currents entering the node are positive and the currents leaving the node are negative, according to KCL, the sum of current entering a node is equal to sum of current leaving the node or exiting out. I1 plus I2 plus I3 is equal to minus I4 plus minus I3. So when we are adding the algebraic sum of currents entering and leaving the node at point A is equal to 0, we can add up all the quantities I1 plus I2 plus I3 plus I4 plus I5. So hence we can see that all the sum of currents entering or exiting a node is equal to 0. Let us consider some examples. Consider the following circuit with node A and B. Currents I1 and I5 enter the node capital A, while I4 enter node B and I3 and I2 exit node B. So I1 is equal to 4 ampere, I4 is equal to quotient, and I3 is equal to 3 ampere, I3 is equal to 1 ampere, and I3 is equal to 2 ampere. So by using the above formula, so if we are calculating I4, applying KCL, I1 plus I4 are entering the currents in node A and B. I2, I3 and I5 are leaving from the nodes. So by substituting the values, I1 and I4, that is 4 ampere plus I4 is equal to 3 ampere plus 2 ampere plus 1 ampere. I4 is equal to 6 ampere minus 4 ampere. I4 is equal to 2 ampere. So the value of I4 in the circuit is 2 amperes. In a more complex circuit, consider the following setup. There are two voltage sources. V2 is equal to 30 voltage and V3 is equal to 20 voltage, along with the three resistance. R1 is equal to 100 ohms, R2 is equal to 1000 ohms and R3 is equal to 150 ohms. Current I1 passes through R1 and I2 passes through R2 and I3 passes through R3. The value of resistances has been given here. R1 equal to 100 ohms, R2 is equal to 1000 ohms and R3 is equal to 150 ohms. So as we observe that current I1 flows through R1, current I3 flows through R3 and current I2 flows through R2 meeting at node V1. We can assume that currents I1 and I3 flows into the node V1 from their voltage sources V2 and V3 respectively. We can also assume that current I2 flows out of node V1 towards the ground. We are applying KCL at the node. Applying KCL to node 1, summation of In is equal to summation of I out. I1 plus I3 is equal to I2. According to Ohm's law, capital I is equal to V by R. Hence we can substitute the currents in an equation with their V by R equivalents to find the potential difference across each resistor. If we calculate the difference between the voltages at each node on either end, this potential difference divided by the resistance gives us the branch current. So 30 minus V1 by 100 is nothing but small I1 plus 20 minus V1 by 150 is nothing but small I3, that is equal to I2, that is nothing but V1 by 1000. By solving these equations, we are getting V1 is equal to 24.53. After substituting the value of V1 in the equation for I1, I2 and I3, we are getting I1 is equal to 0.055 amperes and I3 is equal to minus 0.03 amperes and I2 is equal to 0.025 ampere. As we observe that the value of I3 is a negative value, this simply means that actual current direction of current flow is opposite to our initial assumed value according to passive sign conversion, and the current I3 flows out of or exits the node V1.